Hello and welcome back. Today we are going over maps, one of the most popular data structures and a bit confusing one as well. As I remember, it was to me when I first started learning the concept of maps or hash maps in school. Hopefully this video will help you guys understand the concept of it, and we will dive a bit into detail as well and learn about how HashMap works internally, the concept of hash functions, collisions, and load factors. Before we start, just want to let you guys know that the concept I'm teaching in this data structure series applies to all programming languages and not just Java. So if you guys are working or learning Python, C++, Node.js, or any other programming languages, the concept of these videos will apply to all of them. So what is a map data structure, which is also called a dictionary in Python? Map is a key value data structure. So you basically give a key and it returns some value. In Java, we have three types of map: HashMap, LinkedHashMap, and TreeMap. They all implement a map interface and work the same way with just slight variation on how they store data. By the way, I also have done a series on object-oriented programming where you guys can learn all the concept related to it and learn about interfaces as well. So let's first go over HashMap and let's do a simple example. Let's say we're playing a game and want to assign custom macro keys. For example, let's say we want to do A is for attack, B is for defense. So one of the best ways to do it is using HashMap since we are mapping values. So we have this HashMap class, and you can see it takes in a K and a V. So K is for key and V is for value. So we got to define the types of these. So HashMap, and we got to define the type of our key would be of type string, and our value will be string as well. And let's call our object macro map. And since we're creating a new object, we could instantiate it. So we do new HashMap. Now to assign it, we do macromap dot put. So we have this put method. So put will take in the key and assign a value. So we're going to say put, let's say A, and we can say A is for attack. Let's do one more. Let's say B, we're going to say B is for defense. All right. So the HashMap can store any different types of values or keys as well. We can even store objects in there. If we have our custom object, we can store that as a value and even as a key. So actually, let's just change our key string type to a character because we only have single character here. So let's update this to A character and this to B. So let's print out this map. All right, there you go. So you can see A, this is our key, and this key has a value assigned attack, and this key B has a value assigned defense. So one important point I want to make a note is that our maps cannot have duplicate keys. So for example, let's say I have the key A, right? And let's say this is attack 2. What's going to happen is it's going to overwrite this value. So we have duplicate keys here. We have A there and A here. And what's going to happen is it's going to overwrite this value with the new one, which is attack 2. So if I run this, we're going to see a new value of attack 2 assigned to our key A. However, we can have duplicate values. So for example, let's say I have another key called C, and let's say this is defense as well. Now I can have duplicate values. We will see that. So B, our key B is defense, and then C is defense as well. So remember, keys have to be unique inside a map. If we have duplicate keys, what's going to happen is it's going to take the latest value and assign it to that key. Now, however, we can have duplicate values inside our map. As we saw with B and C keys, we had defense. Let's say we want to get a particular key and return its value. How would we do that? Well, it's pretty simple. We have this method. Let's print it out. Inside our map, we have this method called get. And inside of get, we can see it takes in a key. So let's say we want to get C. And let's run this. We should get, so C is defense, so we should get the value of defense out. All right, there you go. So we got C defense. We have other methods as well. So we have, let's say, if you want to see, does our map contain a specific key? So you have contains. We even have contains values to see if it contains a specific value as well. So let's do maybe contains key. And let's say this is E. So we should get false because we don't have that key. All right, let's do a little bit more complex example. Let's say we want to create a map where you pass in an ID and it returns me a list of strings. So let's create a map for that. Again, we'll create a new hash map, and this time we'll take in an integer. And let's say it's going to be a list, a string. So map string. And let's pass in a new map, and let's import this list as well. So let's say we have our key 100, and that key will return us a list of 3 primary colors. So let's do that. Let's do one more. Let's say we have our key 200 this time. And let's say that's going to return us a list of random names. So let's print this map out. Let me just copy this and replace that with this, and let's run this. All right, there you go. So we have our key 100 here that has values red, yellow, and blue, and our second key 200, which has these 3 names, Chris, John, and Mike. So how does a hash map work internally? It's actually a pretty popular interview question as well. HashMap uses a hash function to map keys in what's called a bucket inside a hash table. When we first create a map, it allocates it with a default load factor of 0.75 and a size of 16. I'm going to explain shortly what this is in a bit. When we call the put method, if I go back to my put method and go inside this method, you can see it's calling this hash function. So if I go inside the hash function, it's trying to calculate the hash value of that key or of that object. So you can see here it's calling this hash code method. Now every object in Java has its own specific hash code. So it's very important when we're designing our custom classes, we should always overwrite the hash code and also the equals method. I'm going to have a separate video on this explaining this. Now there's something called a collision, and that is when a key hashes to the same bucket. You guys will say, well, doesn't every object have a unique hash code? Well, yes, it does. But remember, I mentioned about load factor and the default initial size of the table being 16. The hash code returns a unique value, but then it also takes the table size into account. And because of this, we can run into collisions. In order to reduce the number of collisions, there's something called a load factor, and that tells us how much load or number of keys a table can have before it resizes or increases in capacity. So if I go back to my put method and take a look inside how this is working and scroll a little bit at the bottom, it's calling this resize method. So it's checking the threshold. So that in our case, the default threshold is 16, and our load factor is 0.75 as well. So 16 multiplied by 0.75, that gives us 12. So the moment we insert the 13th element or the 13th key, it's going to resize the hash table and increase the capacity. So in this case, it's going to double it. So from 16, it's going to go up to 32. Now let's go back and see how collisions are resolved or handled. There's something called chained hashing. It's a very efficient way of handling collision. It basically uses a linked list and adds collided keys to it. And I believe from Java 8, the implementation got even better, where if linked list capacity got to 8, it automatically converted into a balance tree in order to increase the performance. So if I go back to my put method and take a look inside this, the logic for it, this is pretty much the logic for handling the collisions. So over here, we can see this treeified threshold. You can see the size is 8. So the moment that linked list size got to 8, it automatically converts to a balance tree. And the reason for that is it increases the performance. So in terms of time complexity, our worst case lookup goes from O(n) to O log n. Again, I'm going to have a separate video on time complexity. It's a bit on the theory side, but it's a very good knowledge to have, especially for backend programmers. That was a lot I mentioned, and to make it easier, let me just quickly demonstrate this visually in Paint. And let's take our first example where we have 3 keys, A, B, and C. So let's take our first key, which is A. It's going to first calculate the hash function for it, and by using the hash code and the table size. So after calculating the hash function, let's say it places it in the first bucket. So over here we have A, our first key, and the value, which is attack. So attack also gets stored here, okay? So this is attack. And now let's say we have our second key, which is B. Again, it's going to calculate the hash function for it, and let's say after that it finds it in the second bucket. Okay, so this was our first bucket, which is at index 0, 1, and 2. So B gets placed here. Now we're also going to have a load factor. So the load factor is always between 0 and 1. And in Java, the default load factor is 0.75. Okay, so it's 0.75. And in our case, in this example, that means that the maximum number of elements that can be inside this table is going to be 3 before it resizes and basically doubles in size. Now let's place our third key inside this hash map, now which is C. So let's say for C, it calculates a hash and that hash comes out to be same as A, as key A. So now here we got a collision. In order to resolve this collision, Java uses something called chained hashing. And basically what it does is it creates a linked list. So over here, it's going to create a linked list and insert this key on top of that linked list. So here we got C. And let's say we got a new key again. Let's say we inserted a new key called D. And for some reason, let's say that D also got a collision. It got placed in the same bucket as A. Okay, it's going to create, append a new node in that linked list and going to insert into that same one. Now in Java, the moment the size of this linked list increases to 8, it's going to automatically convert into a balanced tree. So basically it's going to access out and it's going to convert into a balanced tree. So a balanced tree basically looks something like this. It's going to create a node here, let's say, right? And it's going to start creating this tree and going to place, let's say, A, and then B, and then C, and then so on, okay? It's going to create this balance tree. And the reason for this is purely just for performance. So our worst case time complexity for get goes from ON to O log n, which is much better than ON. Hopefully this visual concept was easy for you guys to understand on how hash maps work internally. And now I want to quickly go over the last two types of map, and that is LinkedHashMap and TreeMap. So let's do a very quick example of LinkedHashMap. Actually, before I do an example of LinkedHashMap, let me do a quick example of a regular hash map that has just a bunch of random keys and values that are integer. Okay, so let me run this. So here we got our hash map with these values. So now let's do an example of LinkedHashMap. So I'm going to create this LinkedHashMap that's calling this class. And same thing, going to do integer keys and values, and let me just call this lmap. And let me copy paste this and do the exact same thing I did for that hash map. So the first one is our hash map, and second is LinkedHashMap. So what's going on here? LinkedHashMap over here is maintaining the ordering of keys in the way they were inserted. And our hash map doesn't maintain any order of keys. So over here, our keys were 1, 400, 125, and 2. You can see the order they were inserted. We got the exact same order in LinkedHashMap, while in our hash map, it did not maintain any order of keys. So that's one of the biggest difference between HashMap and LinkedHashMap. One real-world example of using a LinkedHashMap is implementing an LRU cache, which is a least recently used cache. I may have a separate video on implementing that using a LinkedHashMap. Now let's go over the final type of map, which is a tree map. So let's do the same example we did for HashMap and LinkedHashMap using TreeMap. So TreeMap, we have this class called TreeMap, and same thing, integer keys and values, and let's call this TMap. All right, let's run this. All right, so we got our first is HashMap. This is our LinkedHashMap and TreeMap. Let's see what's going on. So TreeMap actually sorts to the natural ordering of the keys based on their compare to method, which tells how to sort the keys, whether in ascending order or descending. So it can not only sort integer types, but also other types as well. In this case, we were sorting integer types. So here we can see it's sorted by ascending order. So you got 1, 2, 25, 100, and 400. For a LinkedHashMap, it doesn't do any sorting of the keys. It only maintains the ordering of the keys in the way they were inserted. HashMap doesn't do any sorting, nor does it maintain the ordering of the keys. Now, if you want to sort this in descending order, we can. And there's a method called reverse order, part of collections package. So if you go to collections and do .reverse, we can sort this in a descending order. So if I run this, we can see we got 400, 100, 25, 2, and 1. To recap, we went over what a map data structure is. It's a key value pair data structure and is a highly performant data structure as well. We dove into quite a bit of details on how HashMap work internally. It uses a hash function to place keys inside a bucket of a hash table. We discuss how collisions can happen and how they are handled using chained hashing. We discuss the importance of load factor and how it helps reduce collisions by automatically increasing the size of the hash table. Towards the end, we went over other two types of map, LinkedHashMap and TreeMap. They all implement the same methods, and the difference between them is HashMap doesn't maintain any ordering of keys, nor does it sort the keys. LinkedHashMap maintains the ordering of the keys in the way they were inserted, but doesn't do any sorting of the keys. TreeMap does the sorting of keys based on their natural ordering by using the compare to method. Hopefully this video explained the concept of maps, how to use them, and how they work internally as well. It's a very popular interview question as well, so hopefully this video really helped you guys out, and if it did, please do subscribe to the channel, and I will see you all in the next video. Take care.